Hello students, we are starting chapter 3 and this is part 1. We're going to talk about molar mass really briefly and then get into empirical formulas. There are multiple ways to determine the empirical formula for a compound, so just kind of sort that out as we go through this. First of all, molar mass. We've already used molar mass by just looking off the periodic table, for example, for sodium. But if you have a molecule, then what you need to do to determine the molar mass of a molecule is sum up the individual masses straight off the periodic table. So for this compound here, tetraphosphorus trisulfide, what you would do is add up the mass of 4 phosphorus and 3 sulfurs. So 4 times 30.97, which is the molar or atomic mass in terms of moles, grams per mole for phosphorus. You would do 4 times 30.97 plus 3 times the mass of sulfur. When you add this all up, you get 220.09. That's the molar mass. You've already seen how useful molar mass is. It can be used as a conversion factor, going from grams to moles or moles to grams. Another kind of calculation we use is mass percent. This is basically the mass of a single component out of the total mass. So for example, if I had carbon monoxide, which is just CO, 1 C and 1 O, and I want to find the mass percent of oxygen, what I would do is just get the mass of oxygen, all of the oxygen in there, which is just 1 O, so 16 off the periodic table, and then divide it by the total mass of CO, which is 12.01 plus 16, that's 28.01. Divide those, multiply by 100, you get 57.12%. You've already seen how useful this is in terms of the law of definite composition. You can determine if you have a pure substance or an impure substance. Why don't you just practice that? So pause this and determine the mass percent of bromine and calcium bromide. The first thing you need to do is write the formula for calcium bromide, and that'll help you. So I get CaBr2. Calcium is a group 2, always a 2+ cation that has to pair and be balanced with an overall 2-. Since Br is a halogen, it's a Br-, so I need 2 of them. And then to get the mass percent of bromine, just 2 times the mass of bromine, which is 79.90, that gives me 159.80, divided by the total mass of calcium bromide, times 100 gives you 79.94. So quite a bit of the mass of calcium bromide is bromine, just because bromine is quite a bit heavier than calcium, and you have 2 of them. Let's move to empirical formulas. Empirical formulas are different than molecular formulas. Molecular formulas tell you the exact number of atoms present. For example, H2O2, there are 2 H's and 2 O's. Empirical formula is the simplest version of that. In some cases, it can be the molecular formula, but basically it's the lowest whole number of moles, giving the relative number of atoms. So for hydrogen peroxide, H2O2, the lowest number of relative atoms is HO. So if I divided all of this by 2, I would get a single H and a single O. The reason we talk about this is because a lot of times we're working with substances or discover a new compound, and we can only initially determine the empirical formula. Then you can also get, say, the mass of it using something called mass spectroscopy. With those 2 pieces, you can actually find the molecular formula. So say I had a molecular mass of some unknown compound, 34.02 grams per mole. I find that its empirical formula is HO. If I know that the mass of HO, the empirical mass, is 17, you can see that the molecular mass of this unknown molecule is twice that of 17. It's 34. That must mean the molecular formula is twice that of the empirical formula. So 2 times the HO or H2O2. Let's go through one example, our first example in how to determine empirical formula. Empirical formula, you can start out just by writing out the symbols. So we'll be talking about a compound with zinc, phosphorus, and oxygen. You could write out those symbols. And the subscripts, just like H2O2, those numbers give the amounts of moles. So what we're going to do is, starting with this unknown compound that contains 0.21 moles of zinc, 0.14 moles of phosphorus, and 0.56 moles of oxygen. We're going to use those moles, even though they're decimals, we're going to use those as subscripts, and then we'll try to convert those to whole numbers and determine its empirical formula. So let's work through this together first. This is a repeat of the question. The first step is put the moles as subscripts. So just pull it out of the question. 0.21, so zinc, 0.21, phosphorus, 0.14, and oxygen, 0.56. I can do this because in the question here, it says that this compound has those number of moles of those different elements. It doesn't matter what order you put the elements in right now. So the other thing is, you don't see a chemical formula with decimals or fractions. So what we do is we want to simplify it to give whole numbers. And the easiest thing to do is just first divide by the smallest number, 0.14. The reason is, if I could divide everything, and you have to divide everything if you're going to do this, by 0.14, I at least get the phosphorus to 1 whole number. So that leaves us with zinc 1.5, phosphorus 1.04. I still have this decimal for zinc, so the easiest thing to do now to get everything to a whole number is find a number, the smallest integer, to multiply all of these by to get a whole number. So if I have 1.5, the easiest way I can get a whole number is double it to get me 3. So I'll multiply everything by 2, so I get zinc 3, P2O8. And that's it. That's your empirical formula. Sometimes you're not given moles just straight out. Sometimes you're given grams. So say a scientist came upon an unknown compound. He determined that it had 42.05 grams of nitrogen and 95.95 grams of oxygen. How do you find the empirical formula? The only way you could do this is convert to moles and use those moles as the subscripts in the formula. So I want you guys to give this a stab. Pause this, convert grams of nitrogen to moles of nitrogen, and do the same for oxygen using the periodic table, and then put those as the subscripts, and then simplify to get whole numbers if necessary. Okay, I'm going to work through this problem now. Going from grams of N divided by its molar mass of 14, I get 3.001 moles of nitrogen. I do the same for O, and notice we're just talking about O itself, so it's not oxygen, the molecule O2. So I'm just using, if I'm just talking about O, I'll use the 16.00 grams per mole of O, and I'll get almost 6 moles of O. So hopefully you could see you basically have 3 to 6 or 1 to 2. You can put those numbers as subscripts, and dividing by the smallest number, you get NO2. If there's just a 1, you omit it. We don't write 1 for a formula. So nitrogen dioxide. I now want to introduce you to chemical equations. This is an example of a combustion reaction, methane gas reacting with oxygen. This is a classic combustion. You're reacting or burning something in the presence of oxygen. So that's why when there's a fire, a lot of times one of the things to do is to smother the fire to cut off the oxygen supply. This is your fuel here, your methane. This is actually natural gas, and it burns to give carbon dioxide. So that's one of the issues with the fossil fuels. It's always going to release carbon dioxide when you have a hydrocarbon, something with carbons and hydrogens. The other product is water. So notice that this is balanced, and everything on the left side is the reactant. Sometimes you'll hear those referred to as the starting materials. That then proceeds or goes to, shown by this arrow, to the product on the right side of the arrow. Our third way to determine empirical formula uses this type of reaction, the combustion reaction. And this is very useful when you're talking about hydrocarbons. So in this problem, we have a hydrocarbon fuel. Its formula only has C's and H's, and it's fully combusted, meaning it reacts with oxygen, a certain amount of oxygen, to yield carbon dioxide and water. So just to let you know, when we burn something in a combustion analysis, we're using excess oxygen. So even if the substance had oxygen in it, I cannot use the amount of oxygen used to give any information about the oxygen in the formula, just because we're using excess oxygen. So the way that this works is you have a furnace, you put your sample in here, you have gas, oxygen gas coming through to burn it. And then what burns off and is given off is the carbon dioxide and water. So you want to capture that and weigh it. So it goes through certain absorbers to absorb the water, and you can weigh that and get the difference in mass and get the mass of water produced. And it can go through a carbon dioxide absorber, and you can weigh that and see the difference. Other gases like the O2, anything else will pass through. And at the end, you get the amount of CO2 and water, which is critical for us to find the empirical formula. The reason is, and I'm going to go back, I'm going to burn a certain hydrocarbon. I don't care about the amount of oxygen, but what I care about is how much carbon dioxide is produced and how much water is produced, because then I can backtrack. I can go, oh, for every 1 mole of CO2 produced, it must have come from 1 mole of my, or whatever the chemical formula is, the balanced equation is, so many moles of the carbon. Similarly, the amount of water produced, however many moles are produced here, you can convert that to the amount of H, and then that means that had to have come from the amount of H in the equation. So we're not going to do an equation in this problem because we don't use that sort of kind of mole ratio in the equation at this point, but we're looking at the formula, and I'm going to go through a problem like that. So write down these important bits, and I encourage you to pause and try to do this yourself first. Start with this many grams of carbon dioxide, go to moles of carbon dioxide, and then just moles of C. You know how to do that. You look at the mole ratio within the formula. Then do the same with water, but go to moles of H. Okay, unpause, and then I'm going to go through this problem. So the first thing we want to do is convert grams of CO2 to moles of CO2. So I start with the grams of CO2 on the bottom, going to moles on top. So those guys, grams cancel. And what numbers do I put? This is molar mass. So I want to put the 44 off the periodic table, grams on the bottom, and then the 1 with 1 mole, because molar mass is always 1 mole. The grams cancel, and then I need to go from moles of C to moles of CO2 to moles of C. And what are the numbers that I use? I have to look at the formula. For every 1 mole of this whole carbon dioxide, there is literally only 1 mole of C. So it's just 1 to 1. That's mole ratio from the formula. Moles of CO2 cancel. Now I'm left with 0.5253 moles of C. Okay, do the same for water. If you didn't get the first one right, pause it and do the second one on your own. Start with the grams of water. Go grams to mole of water, and that's just molar mass. 18.02 grams in the bottom and 1 mole on top. Then we need to go from moles of water to moles of H. How do you do that? You literally count the number of H's in the formula. So this is because we're just trying to pick out H out of this whole compound here. So it's literally for every 1 mole of water I can count, there are 2 H's, 2 moles of H. Crunch the numbers, you get this many moles of H. And you can see they're almost identical. So it is going to end up being 1-to-1. You can formally just go through the process, put those numbers as subscripts, divide by the smallest number, you get 1-to-1, or CH as your empirical formula. Okay, that ends the 3 ways to calculate empirical formula. You'll have some practice in the activity worksheet as well as the homework.